In this video, I'm going to present to you significant figures. Let's start with the basic concept of significant figures. Before we get into the details, let's understand which word will be more relevant in the context of significant figures. Is it accuracy or precision? Accuracy and precision both are measures of observational error. Accuracy is an expression of how close a given set of readings or observations or measurements are to their true value or actual or accepted value. However, precision tells us how close the data points or readings or observations or measurements are to each other. Now, let me elucidate this a little bit more. Let's consider an example. Let's say we take a shooting area, and in that shooting area, let's say we have these concentric circles that you see. Let's say we have the first hit right here in the bullseye. The second hit is in the third concentric circle, and the fourth hit is on the outermost concentric circle, as you see for this. Now, the goal of the target always is to hit the bullseye, isn't it? So, in this case, my hit 1, this is accurate. Why? Because it hit the bullseye. That's why it is accurate. But hit 2 and hit 3 are not accurate because they are away from the goal or the target, right? Again, taking the same shooting area, but if the hits are like this, none of the hit is in the bull's area. All our darts are in the outermost ring. But this kind of shooting can be called as precise, though it is not accurate. Why? It is not accurate because we didn't hit the bullseye. That is, we didn't hit our goal or target. But why is it precise? Because there is a consistency in our hits. All the hits are in the outermost circle, right? I hope the concept is getting clearer by now. So, if this is the situation, if this is the situation, that is, hit 1 is on the outermost circle, hit 3 is is right in the center, it is hitting the bullseye, and hit 2 is somewhere in between, then this hit cannot be called precise. It is not precise because there is no consistency in the hits, right? As you can see, if you hit the bullseye, if you hit your goal or target, you can be said to be accurate. But if you hit your target, and if you hit your target every time, that means you are both accurate as well as precise. Let's bring this understanding to the scales or to actual measurements. Okay, so all of you have seen a scale, right? So it is a normal scale that we use. It is calibrated in centimeters, and there could be different calibrations, but normal scale that we see is centimeters, and then in between the centimeters you have each centimeter divided into millimeters, right? So there are 10 millimeters in 1 centimeter, right? Now, which one is more accurate or more precise? We will not say precise, because here we are talking about the accuracy of the data, right? And therefore we are going to say it is the scale that has more divisions in it. Okay, the scale calibrated in millimeters is more, rather than a scale which is calibrated only in centimeters. That means in this scale there are no divisions. The least count of this scale, if there are no further divisions to centimeter, will be 1 centimeter, because that is the least distance that we will be able to measure from this scale, isn't it? This scale is actually, this will be more accurate. Why? Because each centimeter is further subdivided into 10 millimeters. That means we'll be able to measure 1/10 of a centimeter using this, and therefore we will say that this scale is more accurate. Mind you, accurate and not precise. Similarly, a vernier caliper is more accurate than a normal scale or main scale. Least count of a main scale is 1 millimeter, as we just saw here. So the least count of a main scale is 1 millimeter, but the least count, or that is the least measurement, or the smallest measurement that you can take using a vernier caliper, is 0.1 millimeter, 1/10 of a millimeter, 0.1 millimeter. Least count of a screw gauge is 1 upon 100 of a millimeter, 1/100th of a millimeter, that means 0.01 millimeter. And this of course is more accurate than a screw gauge, is of course more accurate than a vernier caliper. So I hope the concept is becoming clearer now. Therefore, we can say that significant figures relate to accuracy of data or of the measurement, right? So here we are in the realm of accuracy. Now, let's start with some of the examples. Let's count the number of significant figures, taking few examples. Let's begin with 0.00500. In this, we need to understand a few rules, which I'll be taking up later, but let me first start with the example. So here, the leading zeros meaning the zeros that come, leading zeros meaning the zeros that come before a non-zero digit, meaning this means zeros before a non-zero digit, right? The leading zeros depend on the unit of measurement, and they actually, as you will see, will not count towards the number of significant digits. This part is the significant digits. How? Let's see that. Say 0.00500 is in liters. So we all know that 1 liter is equal to 1000 millimeter. So multiply 0.00500 by 1000. You get what? The zero shifts over here. So you get 5.00 milliliters, isn't it? Same way, if you were to consider kilometers, then the same digits 0.00500 kilometer is equal to 5.00 meters. 1 kilometer equals to 1000 meters. So just multiply that. Same logic, right? So what are these? These are the trailing zeros. Trailing zeros meaning the zeros that come after your non-zero digit, isn't it? These are the zeros that trail the non-zero digit. So the trailing zeros tell us about the accuracy. Now, again, there is a rule specific to this, so please stay on to understand when we consider the trailing zeros and when we don't consider the trailing zeros. Okay, so the number of significant digits here, obviously, if we consider the trailing zeros, that comes to 1, 2, and 3. There are 3 significant digits. Let's see another example, 0.037. Let's use the same logic. 0.037, if it is in kilometers, let's say, then that can be expressed as 37 meters. That means actually we are talking about only 2 significant digits and not 3, and therefore the leading zero can be ignored, right? So the conclusion from example 1 and 2 is that leading zeros, that means all zeros before the first non-zero digit, are not significant. Let's take another example. This has a decimal, 115 point, right? This is a decimal. I've just highlighted this, otherwise it is just 115 and then a point. Okay, that's it. So if we put a decimal after the number, that means no rounding has been done at the units digit. Okay, so this is the significance of the decimal that you see after whatever digits are there. I mean, even if it were 100 and if I put a decimal, then that means that I had not, that would mean that I have not rounded this at the units place, or no rounding has been done at the units place, right? So this essentially means that this number has 3 significant digits, right? Example 4, let's take 70.0. Again, you see a decimal, so see its relevance. This is a trailing zero, but this trailing zero is following a decimal, isn't it? Just have a look at that. So this zero after the first non-zero digit, okay, is significant. Which zero am I talking of? This zero. After 7, the zero immediately after 7, that zero is after the first non-zero digit, that is after 7, and therefore it is significant. Second point is that the second zero, I'm now talking about this zero, the final, the trailing zero, the last zero. This zero we measured to the 10th digit. Okay, this decimal means, when we put a decimal, it means that we counted not just this, there is no rounding that has happened at the units digit. When we put a decimal, that means no rounding has been taken at the units digit, and when we put any number after that, in this case it is 0, that means what we are trying to say is that we have measured this quantity right to the 10th digit, and therefore 1, 2 and 3, there are three significant digits. There are you can call it digits or you can call it figures, it is the same thing. Let's take another example, 300.002. In this, the zeros between two non-zero digits are significant, right? Remember this. And based on all these examples, we are going to form certain rules which will help you master this topic. So count the number of digits, 300002. Obviously, there are 6 significant digits. Let's take another example, 56,000. Now look, count the number of significant digits if you can, and you can pause the video before you see my answer. This was a little tricky. Why? Because this did not have a decimal after the trailing zeros. So it was unclear. It was unclear whether it is an exact value up to the units digit or whether it was rounded to the nearest thousand. So we will consider, if such a case is there, then we are going to consider only the non-zero digits. In this case, it is 56, and therefore we will say that it has only two significant figures. But if we put a decimal at the end of 56,000, like you see on the screen, then in that case, it is an exact measurement up to the units digit. This means that we have exactly measured up to this units digit. So in this case, we will count these trailing zeros, and in this case, it will become 1, 2, 3, 4, 5. That is 5 significant figures or digits. So let's summarize the rules now. For significant figures, all non-zero digits are to be considered as significant. Secondly, zeros in between non-zero digits are significant. Let's see what is non-significant. Leading zeros, that is zeros before the first non-zero digit, are not significant. We have seen all this in the examples, right? Additionally, what is significant? Trailing zeros. When the decimal point is present. Remember, when the decimal point is present, only then the trailing zeros are significant. And what is not significant is trailing zeros when the decimal point is not present, right? Which actually presents an ambiguous situation, as we have just seen before, right? Okay, so if you want, you can take a snapshot of this. I'll just go back. This is the rule, slide 1, and this is the rule, slide 2. Okay, let's carry on. Let's practice some of the examples. Let's do an exercise. Okay, let's write the following numbers correct to three significant figures. Now look here, I'm presenting this with a little bit of a twist. So you don't need to count the significant figures as such, but you need to do the rounding, okay, up to three significant figures. Listen, it is a little bit different from the normal rounding that you are used to. So let's do this practice exercise. It has a little bit of a twist attached to it. Okay, so I hope you will enjoy it. All right, let's begin with this 19.512. Now look, I'll present some of the examples before I request you to pause the video and try some of the questions. Okay, so first see some of the examples with me. So let's take this 19.512. Now look, I had to write the numbers correct to three significant figures, meaning what I'm supposed to do is I'm supposed to round this number up to three significant figures. So it involves counting the significant figures. So I'll count the significant figures here. Obviously 19.512, so it's very clear that it has 5 significant figures. Now my first significant figure is this, followed by 9 and then 5. So I need to do my rounding at 5. Okay, now if I need to do my rounding at 5, then I need to see which number follows 5. Okay, 1 follows 5, so 1 is less than 5, and therefore we will follow the same rules as we use in rounding. So if the following number is greater than or equal to 5, then it is we round it up, and if it is less than 5, then we keep the number as it is, right? You know that. So we are going to use the same logic here. So 1 is less than 5, and therefore we will keep 5 as it is. So here the answer is 19.5, correct to 3 significant figures. Okay, let's see another example. 3.63815. Here again I'll round it to the 3 significant figures, meaning 3.63. This is this 3, the very so this blue arrow, I have to round it up to there, because the following number is 8. 8 is greater than 5, and therefore I'll add 1 to 3 to get 3.64 as the correct answer, correct to 3 significant figures. Okay, let's see the third example. 404.9257. Third significant figure here is the 4, which has a blue arrow beneath it. So following number is 9. 9 is greater than 5, and therefore I add 1 to 4 to get 405. So what I've done is I've actually put 405, and then all the balanced numbers, they become 0. Okay, so 405.0000, which ultimately is equal to 405. That is how I got 405, correct to 3 significant figures. Okay, so remember, there is a little bit of complexity whenever you will see a decimal. So there are more problems that I'll present to you, which will make even that complexity very clear to you. Okay, so stay on. 2.6797. Third significant figure is 7 in this case, which has a blue arrow beneath it, and the following number is 9. Since 9 is greater than 5, I add 1 to 7 to get 2.68, correct to 3 significant figures. Next example, fifth problem, 0.003547. Now remember, the third significant figure here is what? Guess. Is it this 3, or is it anything else? All right, let me answer that. It is not this 3. Do not count the leading zeros. Okay, this will be incorrect if you take the first non-zero digit is this. So the first digit is 3, second digit is 5, third digit is 4. So I need to round this to the third significant digit, that means to this digit 4, where you see the blue arrow. Okay, the following number is 7. So since 7 is greater than 5, I add 1 to 4 to get 0.00355, correct to 3 significant figures. Now look here, it is important to maintain consistency of data. So therefore it is important to keep these leading zeros intact. Okay, we cannot change the value. We cannot put 0.00354 as 0.355 or whatever. I mean, we cannot do that, because obviously in that case we'll be changing the value itself. We cannot change the value, and that is something that I will be presenting to you in the further examples. So stay on and see this very carefully and mind it, please. Let's take this example, 2000.5645. I hope with the previous example you would have identified the first 3 significant figures. Which one? Where do we do the rounding here? We need to do the rounding at this 0, that means the second 0. Okay, why? Because the zeros in between non-zero digits, this is non-zero 2, this is non-zero, so in between if you have zeros, then they are all significant. This essentially has how many significant digits, by the way? 8 significant digits. So the third significant digit is this 0. It is this 0, right? Here there was another trick. Okay, see, even though only 200, okay, count the 3 significant digits, only this part has the 3 significant digits, but if we do the rounding at this, we cannot ignore this 0, that is the third 0. Why? Because if we do that, then we will be changing the value of the expression, of the term given, or of the number given, right? We cannot do that. We need to maintain consistency of data. We cannot change the value. So we are going to retain this 0. So even though we rounded to this significant digit. Okay, let me delete some of the arrows so it becomes a little bit clearer to you. So what I did here was I rounded to this 0, right? The following number was another 0. This is the following number. So since 0 is less than 5, I kept this 0 as it is. Then what I did, that means I kept this 0 as it is. Then what I did, I added this 0 over here as it is. Why? Because had I written 200 instead of 2000, then I would have reduced that, isn't it? I would have divided by 2000 by 10 to get 200. So I would have changed the value. Okay, so therefore I added 0 to get 2000.0000. I just put that, and then all the balance numbers we need to write zeros against that, right, against those numbers. So this is how I got this, and the value of 2000.0000 obviously is 2000, and therefore my answer is 2000 correct to 3 significant digits, right? So this was a little tricky. Keep this in mind. Okay, let's do one more example. 4367000. Now clearly here the third significant digit is 6, isn't it? And again, using the same logic as you saw in the sixth problem, even though I will do the rounding at 6, but I will retain the value as it is. So I did the rounding at 6. 7, the following number, this number 7 is greater than 5, and therefore I added 1 to 6 to get 437. And balance numbers I put all zeros, including that for this 7. Okay, so see, this is the trick. You do the rounding and then you put other numbers so that you don't change the value. It's just that you have done the rounding at the third significant digit. That's it. Okay, but the value does not change drastically, I mean. Okay, it's just rounding. So remember to put the zeros. That's important. Okay, let's do one more example. 2461. This is relatively simple, isn't it? The third significant digit in this case is 6, and the following digit is 1. So 1 is less than 5, and therefore keep 6 as it is. Now look here, I just rounded to this third digit. Okay, and then 1 instead of 1 I wrote 0. Why? And because I did the rounding at the third digit, right? So this 1 is converted into 0. Okay, now look, there is not a major difference between this. Okay, so the values don't change drastically. Okay, since the rounding has taken place, 2461 has become 2460. Okay, all right. Next example, 157.81. Third digit is 7. So the following digit 8 is greater than 5, so I add 1 to 7. So what do we get? We get 158. Now look, what I did was, actually I took this 158, retained the decimal, and then 81, the following digits all become 0 after the rounding. Okay, and 158.00 is actually equal to 158 correct to 3 significant figures, right? That's how I get 158. Okay, let's see the 10th example. 3.681. Third digit, significant digit is 8. Following number is 1. 1 is less than 5, so keep 8 as it is. You get 3.68 correct to 3 significant figures. Okay. Yet another example, 0.003278. Please guess, or please try. Okay, good that you I hope you got this this time. Okay, you got it this time, because we have seen similar problem before. So here the first significant digit is 3, second is 2, third significant digit is 7, following digit is 8. Rounding has to be done at the third significant digit, that means 7, which has a blue arrow beneath it. 8 is greater than 5, so add 1 to 7 so as to get 0.00328. Okay, same logic, since I cannot change the value, we have retained this, and this last 8 has become 0, and the trailing 0 after the decimal, okay, that will not add to this any value, and therefore we just ignored it and got 0.00328. So I hope you are clear on this up to now. Whatever we have discussed, I hope you are very clear about it. Let's do the 12th example, 0.2154. Third significant digit is 5. Following digit is 4. Since 4 is less than 5, keep 5 as it is. And what you get is 0.215 correct to 3 significant figures. Alright, with that we come to the end of this video. I hope you liked it. My name is Vineet and I'm the co-founder of Succeed Easy Tutorials. For more details, and particularly if you want to have a live session with us, please do visit our website. If you like, you may book a free demo session or a free consultation session. I hope to see you very soon in the next video. Thank you for watching.